The first law of thermodynamics says that energy can only be converted from one form to the other and cannot be destroyed or created. The second law of thermodynamics is that the entropy of the universe is always increasing. In mathematics, for a spontaneous process, any process that will take place automatically, the change in entropy for the whole universe has to be positive. The entropy of the universe is always increasing. So for any spontaneous process where A completely converting to B, delta S for the universe for this process is gonna have to be positive, right? And for an equilibrium process where it's possible to go in either directions for the reaction, the change in entropy for the universe is gonna be equal to 0. Based on this concept, we will introduce a new function for any system that is gonna be very helpful to predict spontaneity for these processes or the systems. That function is gonna be simply the difference between enthalpy of the system and temperature times entropy for the system. Is a new function called Gibbs free energy and has the symbol of G. So based on this definition, change in Gibbs free energy, delta G, is gonna equal change in enthalpy for the system minus temperature times the change in entropy for that system. It's known that for any phase transition, which is an equilibrium process, delta G is gonna equal 0. We'll explain why this is the case in chapter 12, but for now, let's take it as it is. So for any equilibrium process, delta G equals 0. So in this case, if we substitute in this equation right here with delta G equals 0, delta H minus T delta S for the system is gonna equal 0, or delta S of the system is gonna equal delta H divided by T. And as we know from the second law of thermodynamics, delta S of the universe equals delta S of the system plus delta S of the surroundings. And at equilibrium is gonna equal 0, which means delta S of the surroundings is gonna be negative delta S of the system or negative delta H of the system divided by temperature. So for benzene, the heat of fusion, this is delta H of fusion, and heat of evaporation is this value here, delta H of evaporation. And it asks to calculate the change in entropy during the transformation from the solid to the liquid, which is fusion, and liquid to the vapor, which is evaporation, right? If you know that the melting temperature is this value here, and the boiling temperature is this value right here. So by definition, delta S of the system is going to equal delta H during the specific process for the system divided by temperature. So if we want to calculate delta S of evaporation for the system, is going to equal delta H of evaporation divided by temperature. So it's going to equal 31 kilojoules per mole divided by the temperature in Kelvin, which is going to be 80.1 plus 273. So it's going to equal 387 joule per mole Kelvin, and it's positive change because it's changing from the more ordered liquid phase to the less ordered vapor phase. So it actually increases the entropy of the system. So delta S in this process is expected to be positive. And just to emphasize, you get the difference between delta S of the system and delta S of the surroundings. As you might recall, we said according to the second law of thermodynamics, delta S of the universe equals delta S of the system plus delta S of the surroundings. And at phase transitions, this is equilibrium, it's going to equal 0. So delta S of the surroundings is going to equal negative delta S of the system. So it's going to equal negative 387 joule mole Kelvin. So as we said, this function, the Gibbs free energy function, is very important to make accurate predictions about spontaneity of any process, because it actually combines the two factors that affect spontaneity, which is enthalpy and entropy. We concluded that the change in entropy for the surroundings is going to be negative delta H divided by temperature. But according to the second law of thermodynamics, the change in entropy for the universe equals the sum of the change in entropy in the system plus the change in entropy in the surroundings. So if we substitute for the value of the change in entropy of the surroundings from this formula into the second law equation, we get that the change in entropy for the universe is going to equal change in entropy for the system minus delta H divided by temperature. And if we multiply this formula times temperature, it's going to give us T times delta S for the universe equals T times delta S for the system minus delta H. We showed previously delta G equals delta H minus T delta S. So that formula here is negative delta G. Negative delta G is going to equal T delta S. What we learned from the second law of thermodynamics is that for any process to be spontaneous, this term here has to be positive. And if this term is positive, that is going to automatically make delta G negative. So for any process to be spontaneous, delta G has to be negative. So if delta S for the universe is positive for a spontaneous process, that is going to automatically make delta G negative. So a spontaneous process requirement is a negative delta G. A negative delta G will mean that the reaction is spontaneous in the forward direction. Positive delta G will mean that the reaction is non-spontaneous in the forward direction or spontaneous in the opposite direction. A delta G that equals 0 means that the reaction is at equilibrium because it corresponds to a change in entropy for the universe that equals 0 as well. So in general, as we said, the two components that contribute to the value of delta G is delta H and delta S, or the change in entropy and the change in enthalpy. So for a process to be spontaneous, we need a negative delta G, and for delta G to be negative according to this formula, you need a negative delta H minus a positive delta S. So if this term here is positive, it's going to become negative with the negative sign here, with the minus sign here, and that is going to add up to the negative value of delta H. So delta G is going to be always negative, meaning that the reaction is going to be always spontaneous. So a combination of a negative delta H with a positive delta S is gonna be a spontaneous reaction at all temperatures, all the time. The opposite is correct. So if you have a positive delta H combined with a negative delta S, is gonna always make this uh, term here positive, or the delta G value always positive, which means the reaction is always non-spontaneous no matter what temperature you do it at. If you have a combination of a negative delta H and a negative delta S, is gonna depend on the magnitude, because if you have a negative value here with a negative value here, smaller negative value that is gonna get multiplied times a minus sign will become positive. So depending on the magnitude of each one of them, if delta H is larger, is gonna cancel out delta S and still make delta G negative or spontaneous, and this is going to happen only at low temperatures, because if you go to higher temperatures, that term will have larger magnitude, so it's going to be a larger positive term that is going to cancel out the negative delta H term and make delta G positive, or make the reaction non-spontaneous. So a combination of negative delta H with negative delta S is going to be only spontaneous at low temperatures. And the opposite is going to happen for a combination of positive delta H and positive delta S. Because again, a positive delta H combined with a positive delta S multiplied times a negative sign will make this term negative. So you need this term to be larger than this one in order for delta G to be negative. So it's going to be larger only at high temperatures. So that combination is going to be spontaneous only at high temperatures. For this reaction right here, these are the standard enthalpy, entropy, and free energy values for the reaction. And based on the sign of delta G being positive, that means that the reaction is non-spontaneous, is not going to take place automatically. And if you want to make a prediction about whether the reaction is going to be spontaneous at any temperature, you can make this prediction based on the fact that both delta H and delta S are positive. So a combination of positive is gonna become spontaneous only at high temperatures, right? So, and it's gonna become spontaneous when the value of delta G switches from positive sign to negative sign. That switch will happen after the value of delta G of 0 at equilibrium. So you want to calculate the temperature corresponding to equilibrium, and above this temperature, the reaction will start becoming spontaneous. So using this equality of the equilibrium condition, the temperature of equilibrium is going to equal delta H at equilibrium divided by delta S. So it's going to equal 177.8 kilojoules per mole divided by 160.5 joule Kelvin per mole. But we have to pay attention to the fact that delta H is in kilojoules, delta S is in joules. So we have to convert one of them to the other. So we probably could just multiply this times 1,000 joules per 1 kilojoule to make the conversion and have the energies in the same units. And carrying out the math is going to give us a temperature that equals 1107.8 Kelvin. This is the equilibrium temperature, or 835 degrees Celsius, if you want to express it in Celsius. Above this temperature, the reaction is going to become spontaneous and it's going to produce a significant amount of carbon dioxide.